I love food analogies. So one way I like to think of cache is like my fridge. If you think of your fridge as like a smaller, faster version of your grocery store that stores food that you eat more frequently, you can think of cache in the same way. Cache is just a smaller, faster version of memory that stores more frequently accessed data from your DRAM or your main memory. I love starting my day off with a glass of milk. So, milk is probably going to be an ingredient in my fridge. You can think of me wanting milk as a load or write to memory. If I go into my fridge and it's there, that's like a cache hit. But let's say today I wanted ice cream, which is food that I don't really eat. So it probably most likely won't be in my fridge. If I look into my fridge and it's not there, that's like a cache miss. So in simple terms, a cache hit is when the data block that you want is in the cache, and a cache miss is the exact opposite, when the data block you want isn't in the cache. In a cache miss, the CPU has to go all the way to the DRAM or main memory to grab that block of memory and put it into cache. Just like how I'm going all the way to the grocery store to get ice cream and putting it into my fridge. The fridge analogy can also be used to explain concepts like temporal and spatial locality. Temporal locality is the idea that if I've accessed this memory block before, I'll probably want to access it again. Cache takes advantage of this principle, which is why we store frequently accessed data blocks into cache. Spatial locality is the idea that if I've accessed one memory location, I'll probably want to access the neighboring memory locations as well. So, say I can't find ice cream in my fridge and I go to the grocery store for ice cream, I should probably get cones, sprinkles, and chocolate syrup because those would go good together. This principle can be seen in action in even as something as simple as looping through an array, as you're constantly accessing data points that are right next to each other when you're doing that. I just got back from the grocery store, I got my ice cream, but let's say I got back and my fridge was full. My fridge doesn't have unlimited space, so I need to figure out what stuff to throw out. In cache management, we face the same exact issue. How do we know which memory block to evict? We can face this problem with 3 different strategies: fully associative cache, direct map cache, and set associative cache. In fully associative cache, there are no rules about where memory blocks can go. Think of a fridge with no labels and no rules. You can put any food item anywhere you want. So here's some paper I cut out to represent cache and memory. And another concept that we have to cover before we can continue is least recently used. The cache will evict the data block that hasn't been accessed in the longest amount of time. Also, here is the instruction set. It consists of only load instructions. Normally, each block would represent a fixed number of bytes, but we'll ignore the details here and we'll just treat each block as a unique address. The first instruction is a load from 0. The CPU checks if the memory address 0 is in the cache. The cache is empty, so obviously memory address 0 isn't in the cache. Block 0 is loaded, and then it's brought in to the fully associative cache. The next instruction is a load from 1. The cache is then checked again. Block 1 isn't there, so it's another cache miss. Block 1 is loaded and it's brought into the cache. The next 2 instructions are a load from address 2 and a load from address 3. The cache is checked, address 2 is not there, and similarly with block 3. Now, the next instruction is a load from memory address 0, but this time it's a cache hit because block 0 is already in the cache, so the CPU doesn't have to go all the way to main memory to access block 0. Since block 0 was just used, it's now the most recently used, and block 1 becomes the least recently used. Now finally, the last instruction is a load from memory address 4, and since it's not in the cache, it's a miss. It tries to put it in the cache, but it's full. Since we're using the least recently used policy, we evict the LRU block. The least recently used block becomes block 2. Fully associative caches are extremely flexible because there's no rules, but that flexibility comes at a cost. The system will have to scan every single address in the cache one at a time, and this comes at an extremely high cost. This is like scanning every single shelf one at a time in your fridge to find the milk. To combat this cost, the next cache we'll talk about is direct map cache. In a direct map cache, each memory address maps to exactly one cache index with no flexibility. For our sake, the way we figure out which memory address maps to which index of the cache is the address modulus the cache size. The first instruction is a load from 0. 0 mod 4 gives us the index 0. The cache is empty, so it's a miss. The next instruction is a load from 4. 4 mod 4 is also 0. We're going to be putting the memory block into index 0. We try to put it into cache, but memory block 0 is already in cache index 0, so we will evict 0 and put 4 in its place. Now the next instruction is a load from memory address 3. 3 mod 4 is just 3, and since cache index 3 is empty, we just put block 3 into cache index 3. The next instruction is a load from block 2, and now comes the last instruction, which is a load from 6. 6 mod 4 is 2, which points to index 2, but block 2 is already there, and block 2 gets evicted. This example shows the defining feature of direct map cache. Each memory block has exactly one place it can go. This makes it fast and simple to check, but it leads to more evictions even when other parts of the cache are unused. It's a trade-off between speed and flexibility. Now, let's walk through how a set associative cache will work. This is a good middle ground between a fully associative cache and a direct map cache. It's a good balance between speed and flexibility. We're still working with a cache of 4 total blocks, but this time it's divided into 2 sets, each set holding 2 blocks. This is what makes it a two-way set associative cache. Each memory block maps to a specific set, but within the set, it can go into any of the 2 blocks. Now, we'll start with a load from 0. 0 mod 2 is 0, so it maps to set 0. It's a miss, so we load block 0 into set 0. Next is a load from 1, which maps to set 1. The CPU checks into cache's set 1 to see if 1 is there. It's not, so it's a miss, and now it needs to load memory block 1 into set 1. Next is a load from 4, which also maps to set 0, and since there's still room, it gets added alongside block 0. Now comes a load from 6, which also maps to set 0, and this time the set is full, so we have to use LRU. So let's say block 0 is the least recently used, so we evict that and load block 6. The beauty of a two-way set associative cache is that each memory block still maps to a specific set, but it has flexibility within that set, reducing conflicts compared to a direct map cache, but staying more efficient than the fully associative design. So next time you're staring into your fridge wondering what to eat, you're not being indecisive, you're just doing cache management.